Okay, hello everyone. Today we are going over a few practical example on classical machine learning and feed-forward neural network. Uh, I copied a link to the notebooks that I'm going to work with in the chat, and I believe in the team. So I think you can open it and we can start together. Uh, in order to make it easier and everyone can see the original file, I'm going to create a copy of this file and we start working on that. So the suggestion is that everyone open the same thing and create a copy and they're on Google Drive so we can start working with the notebook. So I will wait 1 minute so everyone have the time to open the files.
So if you don't have access to the notebooks because you joined later, like they're on the Teams, but also let me know and I'll put it in the chat again.
Okay, so this notebook is going to, in this notebook, we are going to work with Python. And for the Python, we are using a bunch of libraries. Each of them, I try to introduce them a bit. So Pandas, is a library that we use it for handling the data. It's good for handling data like tables, and it has its own structure of storing data. They call it data frame. Uh, so it's very well known in community, and mostly when we are going to work with a big amount of data, usually Pandas is a good option to start with. The second library is NumPy. NumPy is a Python library for working with numbers and uh, vectors and matrices. It has lots of functionalities that we can do the mathematical calculation with it. So almost for those who are working with R and they want to start working with NumPy, uh, if we start working with Python, NumPy is the library that is going to do almost most of the stuff that you were used to do in R. And the other libraries is just not, we're not going to use them a lot. So math for some mathematical functions, operator and random, we're not going, operator, we are not going to use it, but random, so we can delete it. But random, I will talk about it in a second. It's a library to handle the randomness and create random data in Python. We are not going to use this library directly, but because many of the libraries like NumPy or scikit-learn, which we will see soon, they are using random under the hood, we need to import it so we can set the seed. So by pressing Control and Enter together, or by pressing the run here, run cell, we can run this, and when we run it, then we have run all the import, and we have all of these libraries in the memory. Okay. The first step, as a suggestion, and it's a strong suggestion, is to set random seed in any machine learning uh, project that you are going to work with. So, and why is that? Many of algorithms that we are going to use, they use some kind of randomness. So when you run one algorithm to separate time, to different time, there is a chance that you get different results. And we want to eliminate the effect of randomness when we are playing with the hyperparameters and checking, okay, which hyperparameter is better. We are trying to use set the random seed and make sure, okay, everything is not fully random. So if we run the experiment again, we get the same result. So if we don't set the random seed, each time we run it, we get a different result. But by setting that, we are sure that, okay, if the second time, third time I want to run the same code, I would get the same, exactly the same result. So we choose a random seed, and then we set the random seed for NumPy, and also for the random function of random library of the Python itself. We run this. Now we are going to load the data set. There's a data set that we are going to use it for breast cancer. The data set is almost ready, and most of the pre-processing and preparation is done. So here we have the URL, and with pandas, read CSV, because this file is CSV. With read CSV, I'm passing the URL, this function. We are able to read this file, this CSV file, and convert it to a data frame. Okay, let me run it. By just typing the name of the data frame, you can see what's inside. So it has 569 rows or samples and 33 columns. Here we can see the title of each column and etc. We can scroll to the end to see the other columns as well. It has many different components and variables that we can see. For example, here by printing the columns, you can see what column it have. For easy seeing the data, we just print the head of it. So the very first view, the 5 first sample only, to make it easier to understand. So this is the data that we're going. The first column is the ID. The second one is diagnosis or the label that we are going to work with, and the rest of it is some features that is extracted from the dataset for patients. As you can see, some of these values are very small and some of them are very large. So that could be problematic when working with some of the algorithm. For example, in decision tree, maybe not, because the decision tree treats each feature separately, but algorithm like logistic regression or SVM, they are using a combination of these features. So if we scale them into the same range, it would be easier for the algorithm to be able to learn the pattern in the data. Okay, so as first step, as we can see here, let me just print tail, for example. As we can see, we have M and B for malignant, but here we are converting everything to numbers. So with this line, I'm mapping every M to be 0 and every B to 1. Then I create a new column, I call it class, and I use the values from diagnosis. And the ID, it doesn't matter, we are not going to use it. Diagnosis, we already copied into the class. And there's a variable unnamed 32 at the end, which here, you can see it doesn't have any information. So we are removing these, dropping or removing these columns from the data set. Okay, let me run it. And if we print the head again, we see that, okay, we remove the first columns and we add a column at the end is the class label. The first thing that we need to do is to divide the data set into 3 subsets: train, validation set, and test set. You can do it randomly. You can do it randomly. You can choose what sample you want, or you can use the function from scikit-learn. So what is scikit-learn? Scikit-learn is a machine learning library for Python that it has many functionalities and many algorithms that we are going to work with in Python. Most of the algorithm that we already covered is implemented in scikit-learn. So if that's the first step, that's the first go-to when you want to start working with machine learning in Python. So you need to learn how to work with scikit-learn. It's pretty straightforward. It has many functionalities. So I'm using train and test split by passing the data frame that I have, and I ask, okay, for a test size of 20%. So that means I want 20% to be in the test set and the rest, the remaining 80% in the train. Then for the train sets that I extracted, I will do the same splitting. So here I split the train with 2%, and this gives me another train set, smaller train set, and a validation set. So I divided the data frame in 2 steps. The first step to get the test set, and the second step to get the validation set. So here I'm going to print the size of each data set to see what happens. Okay. Out of 500 something data samples that we have now, 364 is in train set, 91 in validation set, and 140 in the test set. But before continuing, let's see what's the distribution of the labels in each of them. Okay, do we have the code here? Yes. Okay, let me just run the next cell. In the next cell, what I'm doing, I'm dropping the class and pass it to X train and just the class column for the Y train. So I separated the labels and the features in X train and the labels in Y train. I do the same thing for validation and for test set. Run it. Here, I get the sum of the labels. Okay, let's first see what's the inside, for example, X train. So it has everything that we had, but it doesn't have the label anymore. And if I go with Y train, it only has the classes. As you can see, it's 1, 0, 1, 0. So what I'm going to do, I'm going to add all of these values together and divide it by the number of rows or number of samples that I have. It gives me a portion of positive classes in this data set. So I do it for train, for validation, and for test. So with the command sum, I get the summation of all the values, and with the command len, with the function len, I will get the size, the number of samples in each of my data frames. Here, as you can see, the first one, which is the train set, has 65% of positive sample. The second one, which is the validation, is 54% positive samples, and the last one, the test set, it's around 60%. So the distribution between train, validation, and test is not equal. Is it problematic? Maybe. In many cases, it could be problematic. We did this splitting randomly. So we want to have a similar distribution between all of them, and we like to have the same distribution as the original data set. So in that case, scikit-learn, the train and test split function, has an argument stratify. So if we pass that argument to both our splitting and we run everything again, the number of samples did not change. I will do the same thing. And here I run the same copy in another cell just to be able to compare the result. So here, as you can see, the distribution of positive samples in all of my train, validation, and test set are now similar. And this is without the certified. So maybe this using the certified is a better approach. For splitting, because this data set was provided by someone, it doesn't have any information. We did the split randomly, but sometimes when we want to do the split, you need to be more careful about that. For example, we don't want to leak any information from training to the test set or from test set to the train set. For example, let's say that we are working with some CT images or some information from patients from different data points. So if we do random splitting, then there is a chance that two data points from the same patient appears in both train and test. Then there is a chance of data leakage. So if we are going to work with such data, we need to do this division, do this splitting by considering the patients. Another approach that we can use is maybe not in our use cases today, but let's say that we are working with the data from a company, and this distribution is going to change over the time. So, and I have the data for the last 5 years. What I usually do is I go with the date for the splitting, and I will keep the last year for the test and the first 4 years for the train set. So these are the strategies, these are the things that you need to consider if you are going to do this dividing the data into train and test. There are more consideration that you have to look into them when dividing the data set. We will try to cover that in the next few lectures. Okay. After data splitting, the first step is pre-processing. So this data set, it's already pre-processed. We already convert everything to numbers. It's encoded. It's not values anymore. It's not text anymore. Okay, that's fine. But only one step is remaining, and that's, as I mentioned earlier, is the difference in the values. Some of them are very small, and some of them, they have very large numbers. So we would like to scale them into the range. For that, again, scikit-learn preprocessing, it has a standard scaler. Well, what does it do? It takes the mean and a standard deviation of the data and convert everything between 0 and 1. So there is a very important point here. For calculating the mean and variance and do this transformation and pre-processing, if we need to get any information from the data, we need to do it only on the train set and not the validation set. So here, what I'm doing, let me just modify this line a bit. And okay. So what I'm doing, first, I defined a scalar, a function, an object from standard scalar. Then I call the fit function on the train set. So now the scalar has the information that I want to use. Then I will use that scalar to scale all of these train validation and tests. So this is very important. We need to fit everything on train set and not test set. And I've seen this mistake in many cases that we do the pre-processing, we do some calculation, we get some information before dividing the test and train, and that causes information leakage. In order to make sure, okay, there is no information leakage, we need to do all of these steps after dividing the test and train. Okay. So I run this. Now if, for example, I want to see what's inside X train, now every value is between -1 and 1. Okay. So I don't have any large number. Every value is between -1 and 1. They are in the same range, which makes it easier for the model to work with. Okay. If there is no question, let's start with training models. Okay. So before starting training a model, I'm loading accuracy score, a function from metrics in scikit-learn to calculate my accuracy score. It's a very simple function, but there are many different scores and metrics in scikit-learn. Based on your need, you can find it, you can Google it, and you can see that there are many different metrics in the scikit-learn that you can use. For logistic regression, again, from scikit-learn linear model, we import the logistic regression. From a class of logistic regression, I create an object, logistic regression or LR here. And for now, I do not use any penalty. If you go to the documentation of logistic regression, you will see that they have many other arguments that you can pass. But here, the penalty we are going to work with. So we see, okay, what are the options for us? For now, we go with none. So after defining the model, we need to call the fit function. This is the same for almost all of algorithm in scikit-learn. They all have a fit function. So we call it logistic regression fit on the training data set, X train and Y train. After training is done, I call this logistic regression again, and this time the predict function, and I pass the X of validation, and it gives me a prediction for validation. And in the last step, using the accuracy score, I compare the true value of the validation and the value in prediction. So let's run this cell and see what happens. So with this setup, I get a performance of 94% on the validation set. Let's try other penalties. Let's start with L1. We cannot do it. Let's go for L2. 96%. So there was some improvement. Again, it doesn't. Okay, we need to change the solver for that. It only works with L2. So between none and L2, we saw that, okay, L2 is working better. So we find one of the hyperparameter that is working better for us. In order to report the result in a paper or to tell someone, we should not report this number. Because with modifying the penalty, we saw that, okay, if I use none, I get 94%, and if I use L2, I get 96%. So if I'm reporting this, the result is not accurate at all. So what I'm going to do is I do the same thing on the test set. So ypred is equal to or predict x test, and then I'm going to print the accuracy score of y test and y pred. So as you see here, the performance on the test set is 95%. So if I want to report the result, the performance of logistic regression on my data set, this value is the one that I can report. And remember, as soon as we get the result, we should not touch the training process anymore, because then that would be considered as a cheating. That would be considered as information leakage. If you optimize the value here in order to get a better performance on test set, that's considered cheating. So we try to get the best performance on validation set. When we are sure, okay, we cannot get anything better, then we go and test it on the test sets. Okay. Now we want to do the same thing for SVM. From scikit-learn SVM, I import SVC. We already saw yesterday that there are many different classes for SVM, and this one is for classification. We are able to do it with different kernels. And let's start with the linear kernel first. And we have cfloat, the regularization parameter. Here the default is 1, so we are using 1, and kernel of linear. The rest is the same. We call the fit function on xtrain and ytrain. Then we get the prediction on validation set. Then we print the accuracy score. Okay, let's see what happens. Good. With linear and C1, I was able to get 97%. Let's change it to poly. So polynomial is not working very good for this example or this data set. RBF 96, okay. Sigmoid 95. And precomputed is another thing that we need to define it beforehand, which we don't have it. Okay. We already tried 4 of these, and it seems that linear is working better. But we didn't touch the C value. Okay. 97%. Let me change this to RBF again. And this time I use another value. Let's say 2, for example. 96, 96, 96, 96, 95, 94. So it's not going to change a lot. Okay. Let's try linear again. 96. Okay, 5. Okay, it seems that the linear with C1 is giving the best performance on validation set to me. So, and just remember that here what I did was I tried a different combination of poly, RBF, sigmoid, and different value for C to see which one is better. That step was called hyperparameter theory. So I tried to find the best sets of hyperparameter to get the best performance on a validation set. Now I want to report the results. Okay, so I create another code and I do the same thing. For on the test is equal to string predict on test set and then printing the accuracy on the test set. 96%. Okay. Now I can compare the performance of SVM with the performance of logistic regression on these two values on the test set. Okay. Now, when I want to compare a bunch of models, report it, I can use the result on the test set. But I'm not going to touch the SVM anymore because now I touch the test set and that would be considered cheating. Any questions so far regarding SVM or logistic regression? Okay, good. The next algorithm that we're going to see is decision tree. Everything is the question is cheating common in the field? And what do you mean by the field? In machine learning community, no, but in other communities that they use machine learning, yes. So I've read lots of papers, lots of reports that they didn't know they cheated. They didn't know that the work is they use some information in the test set during a training, and that caused the result. The result is not reliable. So that's why I'm emphasizing on that, because yes, I'm seeing that people that they didn't have proper machine learning education, they didn't go through the machine learning algorithm, and they just start, okay, let's use a machine learning. And let's see here, using machine learning is pretty easy. You call it, one line, you import an algorithm, you define your model, and then you call the fit and done with 3 lines in Python. So it's really easy, especially in Python, to train a model. But the thing is, can we trust the result? In order to make sure that we can trust the result, there are several steps that we need to consider. One of them is make sure that there is no information leakage from tester to training. Okay. So for decision tree, everything is the same. We have two important hyperparameter max depth and criterion. For criterion, we have 3 options: Gini, entropy, and log loss. We're going to work with these two. And the default algorithm of decision tree doesn't have any max step because they use another hyperparameter, but here we are going to work with max depth. Okay, so I set it, let's start with max depth of 2 and with entropy and see what performance we get on validations. Okay, 95% seems good. I think we can print what's inside the decision tree. Tree. Okay, let's show. Okay, I don't remember the command. So I'm searching. How to do it. Okay. So we need to import the tree, and then we need to call tree dot plot tree dt. Okay. Here we can see how the decision tree is made. The max step is 2. The first feature that is looking is feature number 22. If it's uh, smaller than this value, we go to this branch. If it's larger than this value, we go to this branch. In this branch, we check for feature number 27. And in this feature, we are checking for feature number 26. So two different branch. And let's start with another max step, for example, 3, and see if we get any performance improvements. No, the performance decreased. Let's print the 3 again. Now the depth is 3. The first feature is the same. Now this time in the second level, it's again looking at the same value, and the performance dropped on validations. Let's start with, let's go with max depth of 5 and see what's happening. Okay, the performance is not good. And now let's consider another criterion. Okay, max depth of 3. Okay, max depth of 2. This one, max depth of 2, is not as good as the entropy. And let's now print it. Again, it's looking at the same feature at the first level, but for the second level, it's looking at 2 different features, which is different from the one that we have with entropy. So it seems that entropy with max depth of 2, it gives me the best performance. So remember that I didn't try all of the possible max step or all of possible of combination of these hyperparameter because it takes so long. How we can find this hyperparameter? We should, if we have a good knowledge on how the algorithm works, so and that comes with lots of practices. Then we can say, okay, probably for this specific data set, we can start working with entropy or Gini instead of looking on both of them. And probably I'm looking for max depth between 5 to 10 or between 10 to 100. But if we don't have any clue like me, we have to try everything and see if there is any improvement. That's a bit hard. Okay. Now let's get the performance of this model on the test set. By pred, the same thing. Oh, although the performance here is very high comparable to previous model, but on the test set it's much lower. Now that it's lower, I should not go back and modify it. Okay, let's do it. Let's change it to 5 and then do it. Oh, I get a better performance. Should I report this result? No, because I touched this after I saw the result on tested. So this performance is wrong. Maybe there was some chance that it was working better on test set compared to validation set on max depth of 5. And another thing, whenever I'm running again and again, so as you can see, the result here is changing because there are some randomness in the each time that I'm running, the result is changing. Let me just copy the line that we have on the beginning. And each time that I want to train it, I set the same random seed. Now I run it again and again. Now, as you can see, the result is not changing. Now my result is better. So we see that the random seed here has an effect. And it's if I change the random seed, the performance would be different. What should I do? The best thing that we can do here is try with a couple of different random seeds, let's say 5, and then take the average. This way, we have more confidence that, okay, the performance is more reliable and we can report it. Remember that when we are reporting some machine learning, we are not saying that this model is the best, this model is sorry, we are not selling this model. We are saying this model with this specification on this type of data set with this set of hyperparameter probably is working better. Okay. And when we report it in a paper, someone else read our paper and see, okay, this performance with this model is better working. For example, decision tree is working better than logistic regression. So they are not going to try logistic regression and only use decision tree. They are trusting our result. So if we go with running with different random seeds and taking the average, our result would be much more reliable. So please consider that as well. Okay. Any questions so far? No. Okay. Good. The next algorithm is random forest is ensemble of a bunch of decision tree. So here, for example, we can specify. So the idea is the same. We call it from scikit-learn ensemble. We we call random forest classifier. And for random forest, I would say, okay, the number of estimators, the max step for each of them. So the number of estimators is the number of decision tree that it's using. Max step and criterion, we can use them again. So let's start with one estimator, which the result should be similar to the performance on decision tree. Now I increase it to 2, the performance is going higher. 10, okay, now I'm getting very good performance on the validation set. Let's increase it. Okay, now I get very high performance. That's a bit weird. Let's increase it. Okay, so it seems that with 20, I can get very good performance. Oh, so that was chance. As you saw, the performance of 1 was by chance. And if I do it again and again, sometimes it happens, sometimes it won't. That's why I'm saying we should consider setting random seed and taking the average of that. Okay, now let's print the result on, let me run it with this time, okay, on validation set. Sorry, on the test set. Oh, the performance of on validation set is really high, but on the test set is again low. So that was not a good result here. I can change these values again and again and again and see which one is better, but in any case, it's not considered a good approach to touch the model after reporting on the test. So that was all the examples for classical machine learning. And here we saw that I have to try different hyperparameters to see which one is better. There is a question. Okay, thank you, Matthew. Yes, we will talk about generalizability in the last session as well, in order to make sure, okay, how we can, what is generalizability, how we should choose the test set with all the thing. And yes, in public health in general, uh, using external data set is very valuable to have a good reliable result. Okay. Uh, so going back to the discussion, here we had uh, different hyperparameters that we need to choose, and it's hard. Scikit-learn, it has a model search for you. We call it grid search. And in grid search, you can specify a combination of uh, hyperparameter, and the grid search is running all of them for you and find the best performance for you. But the thing is, the grid search that scikit-learn has is grid search with cross-validation. This CV here stands for cross-validation, which I believe that you saw the definition of cross-validation in uh, the first session. If everyone is remembering, so we can continue. But if anyone doesn't know what is cross-validation, just let me know so we can define it. Because it's using cross-validation and not validation set anymore, here I'm going to do the divide part again. And this time I only separate the train and test set, not validation set. And the rest of the code is exactly as we saw uh, at the top. Okay, I just run it. Now, let's see the code together. So from scikit-learn model selection, we call the grid search cross-validation. And here I want to work with SVM. So for SVM, I specify the different value for C between 1 to 10 to 9 actually. So I want to try all of these numbers, and I want to try all of these kernels. So here I have 9 values, I have 3 kernels, and the combination would be 27. If I wanted to do it by hand, I had to run 27 times manually to see the result, but the grid search does that for me. I specified the cross validation to 5-fold, and I asked the scoring to be based on the accuracy. The search grid, the parameter grid that I want to specify, I specify it here and I pass it here. And the estimator or the model that we're using is SVC. Okay. When I define my grid search, then the only thing I need to do is to call the fit. After calling the fit, I get the best, print the best score, the best parameter, and from the best estimator, which is with the best parameter, I get the score on the test set. So it takes a couple of seconds, and as you can see, the best performance on the cross validation was 98% with the kernel RBF and the C value of 3. But the performance on that was 96% on the test set. That's the value that we can report it. So when we don't know what is the best hyperparameter to go with, a grid search would be a good approach, especially with these algorithms that they are fast. For a deep neural network, maybe it's not as easy because each training will take a couple of hours, but it's feasible to do it with classical machine learning. If there is no question, I would like to jump to the second part of the demo. I'm going to share the link again into the chat so you can open it. Now I do the same thing just to create a copy. This time, because we are going to work with neural network, I would like to modify my notebook to be able to use CUDA and GPU. For that, we need to click on runtime and change runtime type here and hardware accelerator. We choose T4 GPU. When we do that, then the notebook would reset and we need to wait a couple of seconds to make sure that okay, it's connected to the model, to the GPU, and this can start using it. Okay, now we are working with a bunch of different libraries. Let me go through them one by one. For neural network, we are going with PyTorch. Uh, we imported Torch. The name of the library is PyTorch. You can Google it. We have many different libraries for working with neural network. PyTorch and TensorFlow are the most common one. Scikit-learn, it has also neural network, but it's not very flexible. So it's better to work with either Torch or PyTorch or TensorFlow. There are JAX and many other MXNet or many other libraries that you can use, or even in different languages. If you're working with C++, working with Java, they have their own. But the most famous one are Torch and TensorFlow. Here I just import the neural network modules from Torch. I import Torch Vision, which has a bunch of libraries for working with images. Because here we are going to try one image classification problem. Torch Vision, again, transform is some functionalities to transform the images we will see. The matplotlib is a library in Python to show the figures and plot the figures. It's very useful. NumPy we cite again, random we cite in the past. And this TQDM, we call it Taqaddum. It's just for showing some progress bars. It's not related to machine learning. Okay, let me run this block. It's importing the modules. So Google Colab already installed all of these modules. But if you're working on your own computer, on your own system, you need to install these modules beforehand. And most of them are pretty straightforward. You just need to type pip install the name of the library that you want. So these two random seeds are we cite in the previous demo. Now we have a bunch of other settings to make sure that, okay, we remove the randomness. In production, in real world, we need this randomness, but for experimenting and for publication, it's better to set the random seed to remove the effect of randomness in our code. Okay, so for Torch manual seed and also for Torch CUDA manual seed. And this, the last one is when we are using GPU, CUDA and CUDA-NN, they have some non-deterministic algorithm to accelerate work. So in order to do that, we also need to sorry, make sure that we are only using deterministic algorithms. So we run it. And here in this line, I'm checking that if the CUDA is available, I'm using CUDA, I'm setting CUDA to my device. And if it's not available, if this condition, this if condition is not valid, then we use CPU. Here we print it to see if we have access to CUDA. Yes, because we set the runtime to CUDA. If we do not set it to print, the result of this print would be CPU. Okay, loading the data set. From Torch Vision dataset, I'm loading the MNIST dataset. And I'm asking for transform to transform it to Tensor. Tensor is a data type for PyTorch. So they work with Tensor. It's like matrices, it's like NumPy, but they own the data type. We download the data set and train set and test set. Okay. Here I want to see one example to see what's inside. So the label here is 3 for that the sample number 10. And this is the shape of the image that we can see. So MNIST is a handwritten recognition for digits data set. It contains 60,000 samples for test and train. So let's just print another one. This is, for example, 4. And this is the written 4. This is one image. Now we want to classify these images. So we can do the same thing with SVM. For SVM, I just transferring the data set into NumPy format to be able to work with data set, and I'm using only a subset of it because this the data set it contains 60,000 for train set and 10,000 for test set. I'm using only 10,000 here for training and 1,000 for testing to make it faster, because we will see that even with this portion, it takes time. And the code here is exactly the same as we had in the previous demo. So I'm not going into the details, and I'm just printing, running it and see the result. So 89% is the performance of kernel with the linear kernel and C1. We can change it to RBF and see what the performance is. As you can see, it's taking a bit longer for 12 seconds, and the performance is 93%. Okay. That was only to show that it's possible to work with this kind of data with SVM and other classical machine learning. Now we want to go with neural network. This is the rest of this demo is in PyTorch only. So the first step for me is to define my neural network. Here I'm going to define a feed-forward neural network. This should be inherited from neural network modules from PyTorch. Sorry, I'm not going, if you're not familiar with Python inheritance and all of these, I'm not sure if we would have time to cover all of these details. Then here the init is the instructor of this class. We specify the input size, hidden size, number of classes, and dropout. And I created a 3 layers neural network. The first layer is a linear layer from input size to hidden size. And the second layer is from hidden size to hidden size. And The third layer is from hidden size to number of classes. Then this is the structure of my neural network. So this forward is specifying the forward pass. I receive an input X, I feed it to the first layer, I get a variable out. I pass this variable out to a ReLU, nonlinearity activation function that we defined. Then I pass it to a dropout. Then I pass it to the second layer. Then I pass it to another ReLU. And then I pass it to the last layer just for classification, and I do not apply any other nonlinearity on top of that. It's possible, but for the sake of implementation of PyTorch and how they defined cross entropy, it's better to not apply anything on top of that. But if you want to apply it, it should be softmax. So here, as you can see, I only define the forward pass. The backward pass for calculating the gradient and all of those things that we saw yesterday is calculated under the hood. So when I'm working with PyTorch, there is no need for me to take care of the backpropagation because PyTorch is doing it for me. I only need to specify the forward pass. Okay, let's run this cell. Here I wrote a function to train the model for one epoch. So this function receives the model, the data loader that contains the data, a loss function, and an optimizer. Loss function to calculate the loss, optimizer to adjust the weights, data loader that contains the data for me, and the model is the one that we are going to work with. First, we need to set the model in the training mode. Why? Because some layers in neural network, they have different behaviors in train and test. For example, dropout, it has different behavior for train and test. So we need to specify that which mode we need to work with. The number of correct sample, I put it 0. The total loss, I put it as 0. And then for each batch in the data loader, I run these couple of lines. Okay. As I said, تقدم is for just visualization. Enumerate is just for having the number of batches. So it's not important. The data loader, I'm going to explain it in a bit. But this one in each iteration gives me a single batch. So in the very beginning, I set the optimizer 0 grad because optimizer is keeping track of the previous steps during the training. So for each iteration, I need to make it 0 grad. Let me go back and show the picture again. As you can see, the size of this image is 28 by 28. Each of these values, they have, let me just print it, sample 0. So my data is something at a tensor like this. The values are between 0 and 1. 1 are those values in the middle, and 0 are those values in the corner, which means nothing. And the value in between that are not completely white or red, they are some value between 0 and 1. Okay, so this is my input, and the size of it, as you can see here, is 28 by 28. Okay, so here, when I get a batch, my batch, the first part is the input X, and the second part is my label Y. So here, the input, I reshape it to 20 by 20 because the model that I'm working with is a feed-forward neural network. It has only one dimension. When we are going to see the demo on convolutional neural network, we do not need to do this reshape here. But here, because my model is feed forward, is flat, I need to flat it. So I remove this dimension and make it in a single dimension. Then I transfer it to the device, which is GPU, CUDA in this case. And I do the same thing for the label. Here is my forward pass. I pass the input to the model and I get the prediction of the model. With the prediction of the model and the true label that I have, with the loss function, I calculate the loss. I call the loss the backward to calculate the gradient. Now that the gradient is calculated with the backward pass, I call the optimizer a step to adjust the weights. And then for the next iteration that we are going to run, I set the optimizer zero grad to remove all of those gradient that is calculated in the previous step. So this is almost the training loop that we need to do. At the end of each iteration, I keep track of the total losses. So I add the loss of that batch to the total loss to see how was the loss in my training. I get the prediction because the prediction is, as we said, we use the max as a label. So I get the prediction, and the number of correct is the number of predicted is equal to the true label. So I use it to just calculate the accuracy. And in the return, I return the model that is already trained. I calculate the total loss by the length of my data loader to get an average of the loss. And here also, I get the number of correct sample divided by the number of samples that I have to get the accuracy. This is the formula for accuracy. Okay, I'm going to run it. For validation, it's very similar. First step, I put the model in the evaluation mode. I do the same thing this time in order to reduce the calculation, because for validation, I don't want to calculate the gradient for me. So here I specify for torch that, okay, while you are in this block, do not calculate any gradient for me. We can do it. If I remove it, there is no difference in the results that I get. It's only helping me to run this loop faster because it does not need to calculate the gradient and backpropagation backward pass for me. Okay. So with torch no grad, the rest is almost similar. We pass the model, we calculate the loss, and we calculate the accuracy. This time in validation, as you can see, there is no optimizer or to update the weights. Okay, let me run this block as well. Now we did everything. So I defined my feed forward model. Okay, this is the input size. This is the hidden size that is specified, and the number of digits from 0 to 9, 10 different digits is the number of classes. For now, I'm using dropout of 0, and I put the model on the device, which is CUDA in this case. The second thing that I need to define is the loss function. And for this one, I'm using cross entropy loss, which we defined yesterday. And for optimizer, I'm using AdamW to optimize it. So for AdamW, I pass the model parameters that needs to be trained. And I specify a learning rate here. Let me run it. Here again, I'm getting a subset of all the samples that I have to make it just run it faster. 20,000 for training, 5,000 for test. And data loader in PyTorch is a module, is a class that help me to pass the data in different batches. If I need to shuffle the data set for different iteration and all of this, the data loader is taking care of that. So that's why I'm passing the data set that I have into the data loader, and I get train loader and test loader. Okay, I run this. Now we start the training loop. Here I just defined a bunch of empty lists to keep track of the performance for a number of epochs. So here I specify 10. For 10 epoch, I run the train epoch function once, then I run the validation function once, and then I just keep track of, create a log of all the performances of train loss, train accuracy, validation loss, and validation accuracy. And at the end of each epoch, I print and all of the results. Okay. When I talked about تقدم, so this progress bar that you are seeing here is coming from تقدم. So if I remove this تقدم here, we don't see it. It's just for having better visualization. Okay, now we have the result at the end of each epoch for validation set and all of this. Here I just wrote a code using scikit-learn, sorry, using matplotlib just to show summarize all of this information in a figure. On the left, we have the loss, and on the right, we have the accuracy. As you can see, the accuracy on, the loss on train set is going down until the end, but for validation, it's not going down. So here is probably the area that we have overfitting when we are going far from, the two lines are going far from each other. Now let's change the model again. This time I consider, for example, 0.5, 50% for dropout. And we run the same code again and see what would be the performance. Would it be increased, decreased, or not? Okay, I keep these figures and just, okay, now that I added the dropout, as you can see, the difference, the distance between validation and train loss, and the same thing for accuracy, is not high anymore. That means I prevent the model from overfitting, and also the general performance of the model on validation seems higher when we compare it to the train set. As you can see, the train's accuracy was more than 99%, and it was overfitting. But here the performance on train set is around 96 and is close to validation set. So now I have more confidence that there is no overfitting in my training. And so the Adam W is not that sensitive to learning rate, but let's try with very high learning rate and see what happens. Okay, as you can see, the performance is not comparable to what we had. We had around 90%, but now we have around 10%. So that means with learning rate of 1, the model cannot learn anything. And there is not much improvement in the loss. Even if you see my loss, the loss on train set is not decreasing, even increasing in some situation. That means that my learning rate is too high. If we print the figures again, you can see it's going up and down. It's not a good performance at all. Okay, now changing back to another value, 0.5 to see the result, but in the middle, I want to show you something else. Okay, here, let me copy paste this line that we had. We were training the model on Huda. Now I want to just change it to CPU. To just see the speed of training, how much is different from GPU to CPU. Now, as you can see, it's much slower compared to the previous ones because now it's running on CPU. Okay, let me put it back on to GPU. Here we can compare. It's running around 200 something iteration per second, but on CPU it was around 100 iteration per second. I'm not saying that GPU is twice fast as CPU at all. It was only the case with this data set and this model. The data set is very small and toy data set, so the comparison is not accurate. Okay, as you can see, with even a bit lower learning rate, I don't have a good performance, so I stop it, I don't continue it. I reduce the learning rate again. The performance is better than the previous try, but still not as good as what we had with the first learning rate. Okay, let me stop it here. And now I just want to use very small learning rate, okay? And see what happens. If you remember from the very first uh, training module, the first validation accuracy was around 95% and was more than 96% afterward. Okay, but here we are started with 68%, 79%, 83%, 87%. So it's improving, but as we discussed yesterday, it's very slow. So lower learning rate, small learning rate, they might converge, but it takes very long time. High learning rate, there is no converge. So the one of the most important hyperparameter that we need to set is the learning rate. So this is the first learning rate that we tried. And as you can see, even after training for one epoch, we are getting an acceptable performance. Okay, that was the last part of my demo. I think we have a couple of minutes, 4 minutes for any question if you have. Okay. I think there is no question in the chat. And Hussein, if there's no question, I think we can conclude the session.
Yeah, thank you so much, Farhood. It was a great session, and I'll be taking a look at this tutorial as well myself in the future, hopefully. Just before we go, I'm just going to share, actually, I'm just going to stop the recording now.